Okay, before we proceed to the next diffusion relation, I want to do a quick recap on units. And this is just to bring us all up to speed on some of the standard quantities in mostly, Physics 101, basically. I'm going to make a little table here. So here we have our physical quantity, the symbol that we use for it typically. It's unit symbol, and then in the same as in SI units, and then we'll do a physical expression of where this comes from. So let's start out with one of the most basic concepts in physics. It's force. Force has typically the symbol F and uses the unit N for Newton. And that in SI units is kilogram meters per second squared. And how do we typically calculate force? Force is mass times acceleration. Next up, pressure, or also stress. They have the same units. The symbol we use is P for pressure, sigma typically for stress, and the unit is typically Pascal, or a version thereof, like hectopascal or gigapascal. And in SI units, it is Newton per meter squared, which is just kilogram per meter second squared. And so pressure really is, or stress is typically a force per area. Next up, energy or work. Here we use the symbols E typically, or W for work, and the unit symbol is joule. And in SI units, a joule is a Newton meter, which is kilogram meter squared per second squared. And this stems from energy as being the force applied along a distance, r. So you integrate the force times the distance, and that is either energy or work done. And finally, we have power. Confusingly, the symbol for power is also P, so if you have pressure and power somewhere, you got to be a little careful in how you use your symbols. And the unit for power is watt. And in SI units, watt is joule per second, which is Newton meter per second, or kilogram meter squared per second cubed. And so it is the rate of work done, dW dt. So why do I bring all this up? Well, we can always use the units to perform a sanity check that our equations are correct. So for example, we just had Fick's law of mass diffusion. Flux Jm is proportional to minus rho gradient of y. And we know that the units of flux are those of density times velocity, because that's just what flux is. Flux is the velocity of the material times its density. And what are those units? Well, rho is kilogram per meter cubed, and the units of velocity are meters per second. So we have here kilogram per meter squared times seconds. So this is the left-hand side of our equation up here. Now the right-hand side, we have rho. The units of rho are just kilogram per meter cubed. And the unit of y is 1, because y is just a fraction, so this is unitless. And as a result, the units of the gradient of y, which is essentially dy dx, is 1 over meters. So the right-hand side here has the units of rho gradient y, which is just kilogram per meter cubed times 1 per meter. So as we saw from the last video, Jm is minus the diffusivity d times rho gradient of y. And actually, let me replace diffusivity d here with kappa m, since this is what the textbook uses. Diffusivity kappa. And we find that the unit for kappa is the same as the unit of Jm divided by rho grad y. So that is kilogram per meter squared second divided by kilogram meters to the power 4. So that is meters squared per second. That's the unit of kappa, of the diffusivity.